We've updated.
All right.
Your introduction.
Yes. Welcome. This is the monthly meeting of the Robotic Society of Southern California. My name is Ben. I am the current president. And welcome. Today we have two great talks. The first one, Alan will rejoice us uh, with his introduction into the humanoid, full-size humanoid world with a talk on the Unitree G1. And he thinks we're gonna try to talk him out of it. After that, Mr. Nathan Lewis, if you guys don't know who that is, he will be giving us a talk on the role of Magellan contest. He was a multi-year gold medal winner of the contest, so he's gonna give us a good talk on his hopefully his bills and Jim.
I just got a notice from Nathan. I'm terribly sorry and embarrassed, but he's ill this morning.
Uh-oh.
Can't give the talk.
Okay. Well, so I mean we'll figure it out. Alan, can you give us maybe a 1.5?
I can step in if you want to.
Yeah, you can take some, which is perfectly fine. Otherwise,
cramming all this GPS stuff.
We've got a fully charged robot. So we have a couple. If you want to take the last hour and a half hour.
What half hour? Yeah, whatever you want.
Okay.
All right.
That's
whatever you run when you run out of stuff.
So we're gonna switch it up a little bit.
I don't have to worry though.
Nathan did a talk at the on YouTube.
Okay. Yeah. Hopefully we can schedule him in for a future month. Hopefully he feels better.
I'm sure he will.
Yeah, I just saw that in the mail because he's not online.
Okay.
So after those talks, we'll break for lunch for a little bit. Come back and do a show and tell where anybody can. Sorry. At the new format. The new format. At noon, we're gonna do the show and tell, where anybody can bring in anything that they're working on and show it off and amuse us and impress us. After that, it's just lunch and everything goes. So Alan, if you're ready.
All right, perfect. Thanks, Ben. At last month's meeting, I had talked about how my Alfie had caught fire, and I had to replace the buck down converter. And actually, I used that as an excuse to do a partial teardown. I wanted to print a new base that brought the torso forward another centimeter to try to find that center of balance. I took the wheels off and I designed and 3D printed inserts so that the wheels are at a specific height and they don't bounce around so much. Life was good. And then about 3 weeks ago, a YouTube video of this guy dropped. And that's pretty much all I've been able to think about ever since. So I'm always happy to talk about the stuff that I'm working on. And for this past month, I have been working on recreating their articulated hands, which we'll talk about in the last half. But I thought it would be a very good use of our time. Actually, I have two goals. Number one is to explore the hardware platform with everything we know, everything we can guess, and talk realistically about what this would need to, have it in your home. The second goal is I'm scheduling this as an intervention so you guys can talk me out of making a really bad financial decision.
How old is your car?
Right? How many kidneys do you need? You can cash out your 401k. There's no financial penalty for that.
Who needs to retire when the robot will be doing your
I'm single. I don't have any kids. What else am I going to spend money on?
Well, 401k cash out is a taxable event. Just so you know.
Walter, can you just blurt out YOLO? Okay, so far you guys are YOLO. You're being very supportive, and I appreciate that. Unitree is the same folks.
Camp is on.
Oh, Camp's on? Hey, Camp.
Hey, Camp.
Good morning.
Easy for me to spend your money, he says.
It's afternoon here.
All right, glad to have you. These are the same guys that built the Unitree Go-2. It's the robot that's sitting on the table behind me that will take it through its paces during the show and tell. They've been making quadrupeds for about 7 years now, and they're good at the hardware. The Go-2 uses the 8-year-old MIT Cheetah software platform until recently, which we'll talk about in a minute. And this one they have available, the basic radio controlled version for 1600. It is very easy to hack. So they locks a lot of the advanced features behind software paywalls, very easy to get around. And so these are the guys that announced the Unitree G1 starting at 16,000. Now I'm not saying 16,000 is cheap because it is not. But in the discussion about humanoid robots and a dozen companies that are vying for your dollar, no one except for Agility, Robotics, and Digit have even mentioned the price. Elon suggesting that it would be the price of a car, which everyone naturally assumes to be about 25,000. But I need to remind those people that Elon's company, Tesla, they do make a $35,000 car, but they also make $120,000 and $60,000 cars. And he tends to exaggerate a little bit. So I like to put on my prognostication hat for a little bit, seeing these full-size humanoids. I see them being available in retail starting at maybe $120,000 to $250,000. The lower cost ones, they're going to recoup their costs by a subscription model. So all of these things are working through the magic of reinforcement learning. And that iRobot future where all the robots are connected and update automatically and a skill learned on one side becomes available to all, that is going to be their subscription cloud model. You'll subscribe to their cloud, your robot will get new capabilities every day. And just like the Aldebaran Robotics Pepper robot, only $2,400, but you have to sign a contract for a 3-year software subscription at, what was it, $600 a month, $400 a month? So it ended up being a lot more. So the fact that they are announcing and have a prototype ready of a $16,000 robot that's this performant is nothing short of amazing. And ever since they announced it, my inner 10-year-old boy has been screaming at the top of his lungs, "You need to get this." At the same time that they released the video and updated their main website, they also have a shop order page, but they haven't made the robot available on the order page yet. $16,000 was the price that they announced, and they'll stick to it. I don't know if the shipping and handling is going to be 400 or 1,000 or what. And 20% import duty could tack on another, right, to walk the dog, another $3,500 depending on configuration. But
right, at the same time as the dog, it might be less.
Right, if they have like a bulk discount. So they did release in their video how it stands up. They couldn't copy the Boston Dynamics one exactly, but I'm almost certain it could get up in the same way. As we scroll down.
I just see that in the chat it says you need a humanoid to walk the dogs. They sell them as a pair.
How do you program it to do tasks? Like, what if you wanted it to clean the shower?
Right. So that's the thing is the cheap
$100,000
is probably going to be radio controlled. It can't do that.
So it's not.
And the breakthroughs required for more general tasks are still being made. We've seen hints of it with other humanoid robot videos, and that's exactly why there's 12 companies now spending tens of millions, hundreds of millions of dollars developing the hardware platform because they believe the software is going to catch up.
But that'll take time, as we hear from Chris Albertson likes to say. The software is the hardware is the easier part.
Yeah. So they've got some video clips. They control the baton. what is impressive about this isn't that it's twirling a baton by itself, but give you a little glimpse into what it takes to do this without falling over. Up until the reinforcement learning and Isaac Gem stuff, they would generally code an MPC controller just for the legs for locomotion, and then a separate controller for the arms. Full body robot control, we knew was the next step. They knew was the next step, but they didn't have a solution yet. So what you're seeing is not only that it can swing this baton around, but it is incorporating the full body dynamics that keeps it upright and keeps it in the same position. So there's a lot hidden in some of the videos. So they have a quick demo of, oh, it's not even going to show you the full thing, of crushing nuts. I do not want it. That is not a task that I think is very.
Hey, can I have a Coke?
Yeah, powering its finger.
Yeah. Well, yeah. I don't think that's but yeah.
But the hardware itself is performant, right?
But you can solder like nobody's doing.
Yeah.
Just like an engineer.
And so here's what ticked me off about it. Was that the $16,000 version of the robot has mannequin hands with gloves on it, right? They're just the wrists rotate at the top, but there's no grippers. And I'm like, man, if I'm gonna dump 16 grand into a robot, I want fingers that work.
Yeah.
And so that started on my every waking moment after working on the weekend task of recreating the hands that are 3D printable so that when I can buy this unaffordable robot, I can slap on my hand design and it'll work. So the last half of my talk, I'm going to show you some tricks and things that I did for those. And so far, everything looks great. So that is where my adventure started, was right here. I wanted hands and I didn't want to spend what we thought was maybe $40,000. Switching over to the price sheet, certain qualified buyers were sent a pricing sheet for the robot. The information here on the first tab is the same thing that we saw on the website. 1 degree of freedom waist, 1 degree of freedom wrist, which is up at the top of the forearm, no moving fingers. They call it a high performance 8-core CPU. It has to be using the same system module that they have in the Go2. It's a Rockchip 3588P, or maybe it's an S. 8 gigs of RAM, 32 gigs of flash. No programmability. And so there's really, I would say, not an option for reinforcement learning, but I'm going to show you something in a second. To get to what the higher cost ones are, when you go up to $33,000, you get a 40 tops Orin companion unit for AI support. They up the knee torque and payload. That is not a hardware enhancement. They're just software unlocking the additional force. Because remember, with low gear reduction BLDC motors, you can limit the force applied, and they relax those limits when you spend twice as much. Now, when you go up to 35,900, you get for extra $2 grand, you get the 100 teraops Orin version, which is that's a $2,000 development unit. You can buy them retail. You can buy them from NVIDIA. But the one you can buy retail won't fit in the body cavity, which we'll also talk about in a second. It is only when you get to the EDU Plus that they add the additional 2 degrees of freedom in the waist. So if you think like the Boston Dynamics and the other one, to be able to twist left and right and forward back, something that's hasn't been seen yet because I don't think they've done it. And it also includes the 2 degree of freedom wrist, but still the mannequin hands. It's only when you go up to 55,000 that you have the 100 joules GPU, you've got the dexterous fingers, everything on it. And then above that, they have multi-array touch sensors available for it, something else that they haven't done yet, because if they did, we'd seen it, that are available for an additional cost. So in order to get the full Dream robot, have your Visa or MasterCard handy, it's going to be 55 grand. Getting back to,
Alan, were those lower models upgradable too? Like the waist, for example, that seems like it's kind of built in or not.
It's built in or not. The pricing list suggests that at time of ordering, you can mix and match the different features. Like it would be possible, it looks to me, to order let's just say the base model with the 2 degree of freedom wrist. That being said, the base model controller may or may not be able to control it. But yeah, once they're ordered, I don't think there's a way to upgrade the wrists or the waist to anything more. But 10-year-old me, $16,000 robot, you don't need to eat. So about the time that they released it, they actually updated their GitHub site with the URDF and Mujoko models of the G1. So this can be brought into Omniverse or the standard raw simulator, which name escapes me because I don't use it anymore, Gazebo. This also put Mujoko on my radar. Mujoko
what are you using for a simulator these days, Alan?
So I am a big fan of Omniverse. The hardware requirements are a little bit higher, but I absolutely love it. It's a dream to work it with. It's
that's NVIDIA, right?
And the environment is everything that Gazebo isn't. You can edit the robots through the UI. You don't have to edit a text file. And that's one of my biggest gripes about URDF and Gazebo is that they never made a GUI for editing and creating URDF robots. You always have to do them somewhere else or write them by hand. Omniverse, you can import from several different sources, articulate. But the one that Unitree uses, you're
calling that UDERF?
Sorry, I'm getting too excited. I'm talking too fast.
I'm catching up with your lingo there. I like it.
Omniverse Isaac Sim is amazing to work with if you've got an RTX graphics card that supports it. The Unitree guys, and I could have sworn they were on stage with the NVIDIA presentation for Groot and NVIDIA Omniverse and Isaac Sim, but maybe they weren't. These guys are using a Google DeepMind simulator called Mujoko. And so they also provide Mujoko definition to do reinforcement learning over there. And the STL files that are a part of this model are what I used for geometry reference to recreate the original hands and then to structure the basement, which we'll get to in the last half hour or 20 minutes or so. With this running in the background, no, we will not do that. I do not want that. I want this. There we go. There's a company in Korea is a reseller who has a prototype unit available that they're demoing to their board members. And so while this is running in the background, I wanted to talk about this robot and humanoid robots practically over the next 6 months to 2 years. And one of the first things that I wanted to talk about is let's table for the moment the fact that the software breakthroughs require this to be truly multi-step learning aren't here yet, but are en route. So let's just assume the software is available. Okay, it's a stretch, I know, but I want to focus on the hardware. So you have force feedback, you have load feedback on each of the joints, 2-hour runtime. One of the first things that I want to talk about with you is, and you'll see this when you get up close and personal with my Go 2, is there are little scratches and discolorations all over it. It's hard plastic, it's metal, it's been operating in my house. And even with a skilled human pilot and the fact that it has obstacle avoidance and a LiDAR, it bumps into stuff. And when it bumps into stuff, it scratches itself, it scratches the other stuff, it scratches the walls. And at least with the quadruped, if something fails, it'll just drop down. If a humanoid robot fails, aside from the go crazy and grab a knife type scenarios, it's just going to drop. And these are a lot heavier than my quadruped's, I think 25 pounds. It's a hefty boy. This guy is 35 kilos. And so it's capable, you can lift it, but if something goes wrong, just to your house and environment, kids, pets, the the penalty for failure is a little bit higher, which is something that you're going to see with any of the humanoid robots, right? So my first point is piloting my go-to around my house. I still bump into stuff. What hope does the humanoid robot have to not bump into stuff when a skilled pilot still does it? So that's one thing to kind of think about as we move forward into our robot overlord future. The second one is that this robot comes with a 9,000 milliamp hour battery that they're claiming has up to 2 hours of battery life between charges. All right, so you're not working in a factory, you're not doing a lot. That seems really, really, really short. And so I started digging into why that might be. And looking at the video and taking the proportions, it looks exactly like the go-to battery that I have the go-to. Go and pass this around. Please don't drop it if you can. So this is the so this is the go-to battery. This go-to battery is a 6,000 milliamp hour battery. Now they also have a high amperage version of it with 1,500 milliamp hours, the high capacity batteries that fits in the same envelope. Right. So my first thought was,
You don't need a hit.
why? First off, why wouldn't they use the 15,000 milliamp battery? And secondly, if they're using the lower capacity battery, why wouldn't it just be the same capacity as the base model Go-2 at 6? This one's 9. It didn't make any sense.
Are they different voltages, maybe?
I think they're the same voltages, but we'll have to look that up. And so naturally, I took my model of the Go-2 battery and I drug it into the chest piece. And my first thing, I'm like, oh, look, the battery fits. I wonder if I can just buy, just naive me. And then I started thinking about it. So this is the chest cavity of the G1. Now, if you're looking at the battery, look at the thing, the first thing you notice is the G1's tiny, right? So this takes up 1/3 of the chest cavity the full-size battery does. And then you start thinking about, well, the motors for the arms will come into about here. So there's a slight sliver of room maybe between the arms. And all of the space down here would be taken up by the optional 3 degree of freedom waist, the 2 additional servos and the mechanism to lean and twist. Where'd the electronics go? And then I realized, and that this is all conjecture, but I'm willing to bet you lunch on it, is that the reason that they're offering a $9,000 9,000 milliamp hour battery is because the battery in the G1 is not the same size, it's shorter. So if you, just proportionally, if you take the base battery at 15,000 milliamp hours and you divide by 15 and multiply by 9 and use that as the width or depth as a rough measure, the battery on the Go1 is probably shorter. They're probably using high capacity cells in a shorter stack, and they're using the space between the battery and the other side of the robot for the main control board and for the optional Orin with a fan. And there's no room. So aside from battery breakthroughs or plugging it in, which they've done for their demos, you're going to be limited to 2 hours of runtime. So okay, so at least now we understand why. So that's good. Good. It's a little smaller.
Yeah, we saw. Everybody's.
So the second thing that I wanted to get in front of you, along with the same subject as the battery life, and this is something that's going to affect all humanoids, is so you run it for 2 hours. What do you do with the robot? Where do you put it? What happens to it when you power it down to charge it? This battery pack needs to be removed from the unit for charging. They're claiming in the mid to upper NU that they have a docking station that no one's seen yet. I'm sure they're going to have one, but what would that even look like? So with my Go-2, when it's time for a charge, I just back it up underneath my desk and it sits down, and then I turn it off. Very easy. It has a default stable position where it can sit and it's not bothering anyone. It fits underneath my desk. I was going to trip over it. Let's get back to this video for a second. Let me move this back over. In addition, I want to point out a few more things on the video, and you'll see this in almost every video of the G1. Notice how the tech, and it's the same technician, is always holding it by the neck. Now, they have demonstrated that you can kind of steer it. They're taking advantage of the balancing algorithm to move it around, but that's not why he's holding it. He's holding it because, if I were to guess, they've coded the walking program just like they did on the Go 2. It's not a reinforcement version of it yet, and it's not stable. There's a reason it's only been recently we started building humanoids, and that's because until very recently, no full body controllers. Every programming method to get it has always been static with code. It's just not quite ready yet. But moving forward to when it's time to power it down,
they do let it walk, like you saw there. For it,
oh, yeah. Someone
how
do
they
hand off of it?
how do they know when to do it and when not to hold
Well,
it?
he was the developer was planning on, or the engineer is planning on holding it the whole time, and then someone in the room said, "Can you please take your hand off the neck?" And then he's like, "Okay, but please move slowly."
Well, this was a demo.
Yeah, you can hear it in the audio when you.
It was in English too.
So, and this is one of the things I wanted to get in front of you, and this is all humanoids, not just this guy. So it's time to power it down. And so he kind of steers it in front of the chair. He presses a button on the controller. Of course, we have to flash to the website back there, authorized partner. He gently guides it into the chair. He presses another button to power it down, and then he carefully leans it back. A couple of things to point out here. Notice he's not trusting the chair to hold it up. That's because it's got a smooth bottom. It has a smooth bottom, and once it's powered down, there's no tension in any of the joints. So you're not really going to trust it to sit in a chair. You know, you could rely on the fact that the back of the head is shaped like a hook to maybe catch it if you want to abuse the LiDAR back there for a little bit. And yeah, Bill, it is not yet dynamically stable. And I want to get something in front of you as part of that in a few minutes. Is what do you do with the robot when it's charging? So do you have it sit back down and lay down? Do you have like a murder scene in your home office every time you lay down? Do you fold it up? There's
standing like holder, like a a dock, standing dock.
Yeah, and this is all of the robots. Maybe some of the other robots allow you to plug in to charge.
The noose. You can have a
seems
noose.
like it seems like it could just fold around in some funky crouching position. You know, we saw it get off the floor. Why couldn't it just kind of squat over?
Except that there's no hard locks on the joints, and there's no tension in the joints once it's powered down. So like in some of the movies, you'd see where like when you lose power, it seems to settle into some kind of a rigid position. It's not there. The joints just are floppy. It goes full floppy aluminum robot. So for all of these, do they stand 24/7? What do you do with them when they're charging or when they're powered down? Now, thinking ahead of this, because 10-year-old me is screaming for it, like, well, what if you designed and built a wall-mounted thing with a little cubby hole that could capture with a slight up your turn, maybe 6 inches lower from the standing height, and then some type of a motorized like roller coaster thing that could come down. So it would capture it, it could relax, and it couldn't go anywhere. So I'll probably draw that up over the next couple of weeks, but no one's answered that yet. What do you do with your robot when it's charging? It's not realistic to have it stand 24/7. That's unnecessary wear and tear and heat on the leg joints.
And lying down it takes up a lot of room and
yeah,
it's kind of
exactly
awkward.
Yeah. My dog fits under a desk. This guy would just have to lie on the floor with cones. Maybe the cones I bought could lay the cones around him.
Well, like that other robot, the new Atlas Electric, whatever, how it folds up onto the bench really
That's
tight.
what I meant, something like
that one folds up and the person like picks it up like a piece of luggage.
Oh yeah.
Why can't this one do that? And then maybe there's like Also, there could be a mechanical lock to hold the legs
Yeah.
together or something, just a mechanical lever or a thing that, so that it won't come apart, you know?
I think I'd hang him on the wall, because he
Or
loves
hang him
he'd be
on the
hanging
wall.
on the wall, just.
Yeah, put it like a hook on the
Like
back.
that, he's carrying it, but maybe it's on, so that's why its joints are stiff, because it's
Yeah,
turned on.
Yeah, so it's currently energized.
Yeah.
So there's in the video, there's the position where it folds itself into this ball, and then the engineer picks it up to demonstrate that it's not too heavy to pick up, but it's still powered on. So anyway, it's something to think about. What do you do with your robot when it's charging? My guess it's going to be some type of a wall mount scenario,
Yeah, well,
so that they don't have to pull down, lay on the ground, or
that's, yeah, I think that you're right, the wall.
So
Take
they'll
up space that
probably
way, too.
Standing is the way, is kind of the best
You
way.
could go lie in a bed.
and then go.
Yeah, it could, like
Yeah, you
humans
get a bed.
lie in a bed, but that takes room.
Yeah.
We need two robots. You need two robots now. The other one's charging. Right?
Why buy one when you can buy
Just go
two
to-
at twice the price? You guys are so supportive. I appreciate you.
I think
Yeah.
like the cubby hole, just like in you know, Denzel Washington's movie, that old movie with you know, the robots are in like a cubby, I think, and it's like it's supported in there. So you need a special closet.
Yeah. Put them in the closet.
So the last kind of the things we can draw some conclusions from is up until about 2 months ago, all of their code has been for their quadrupeds has been rigid MIT mini cheetah derivative code. Maybe they add a couple of things to it. It's been the traditional method of quadruped software development, and it works. My nickname for him is Stompy right now because that's just the walking algorithm, and that's the way that it approaches movement. About 2 months ago, they released an update for the higher level robots, because again, paywall, that they're calling AI mode. Now, behind the scenes, they have an entire module that handles the high level control functions that they call sport mode. And so that's the one where you feed it commands, walk forward, strafe left, do a trick. And so when you switch to AI mode, it lies down, it switches to this other module, and then it re-engages. Now, my best guess is that their AI mode is they've been using the gym and reinforcement learning to train a series of behaviors, and that they figured out how to quantize, reduce, and stuff that resulting model in the NPU on the Rockchip 3588. That's the only thing that makes sense to me, unless maybe they have a discrete whole number engine or something that just happens to be performant enough to work. But I guess we're doing this backwards. During the show and tell, you'll get a firsthand view of Stompy. In AI mode, the walking and the movement is smooth, and its recovery from disturbances is smooth. And so there's no doubt they're going to be doing something similar on their G1. But in order to do something like mine doesn't do it like that. Mine, you knock it over, it notices it's knocked over, and then it has a hard-coded stand-up routine. And this is the mode that supports the handstand that they teased in the first promotional video last year. So Unitree is working on it. I expect to see something similar if they can get the full body reinforcement learning model to run on the NPU. So it might be able to do a few more things, but really to do, I think that's going to be limited, and you'll need a fully like Orin level or next generation after that to do the truly useful general purpose, teach it a new task, robustness stuff. What I wanted to chat with you about is, so naturally I brought the STL files into Fusion to take a look. This version has my hands and forearms on it. And just to give you an idea of scale, here's a person. The robot itself is only 4 foot or 4'2", depending on how high it stands. So it is small. The hands are oversized for its body. So it will be limited in terms of the things that it can do. It'll be challenging to reach on the countertops. It can't reach very high in the refrigerator. So it is going to be limited by its height, which is another reason why it's only 16 grand. But what I wanted to chat with you guys about is looking forward, assuming that the hardware, the software is able to keep up, the hardware platform itself, what things would this hardware platform be capable of? Right now, I'm just thinking of the simplest stuff like a shake hand that really shakes your hand, or a high five. Um, should it be able to walk upstairs with a handrail? Yeah, it should be able to do that. Can it open doors? With the articulated hands, it should be able to grasp and twist doorknobs and door handles. So the promise for humanoid robots is to be useful. So having a 4'2" robot in your house, everything that I can think of is limited to the same things that you'd ask a 6-year-old to do. But looking at the hardware alone, you have the trite, get me a beer. Can it open up a refrigerator door? Probably. Can it grab something off of one of the lower shelves? Absolutely. So the get me a drink, get me a beer contest, the hardware should be capable of that. You've got that in the bag. Having a robot in the house, limited payload. Could it carry a laundry basket? Maybe. I think it's limited to 3 or 5 kilograms most. So just looking at the hardware and the 3-fingered hands, here, let's get rid of our stand-in here. So it has 3-finger hands, the thumb pivots. There's load sensing for the motors. You have a rough idea.
Those are your hand designs?
Yeah, we're going to talk about that in a few minutes. So I have a rough approximation of force by virtue of load. So it can't tell if there's a light touch, but I can, the motor controller I'm planning, the motion flow I'm planning for it, you can express in terms of speed, velocity, position, and load limit. So looking around your house, if you had a 4-foot tall, 4'2", 4-foot humanoid in your house, what else do you think the hardware would be capable of doing? If it's useful, great. If it's fun, I don't know if the legs are strong enough to crouch down so it can reach the ground. I'm hoping that it does. Picking stuff off the floor, picking up after your kids, tidying up toys. Hey, take these glasses into the kitchen. I think it can reach and put it on a counter, but it's not tall enough to set it in the sink, and I don't think you want things dropped into the sink. Set things into the dishwasher. It should be able to open the dishwasher door. Are the arms long enough with the legs set up that they are to be able to maintain balance and to reach into a front-loading washer and dryer? Maybe.
Tim, when I think about mobile robots in the home, I think of the big 3 jobs: food, clothes, and trash. And we got dishwashers for washing dishes. We've got washing machines for, washing the clothes. We've got trash compactors for garbage. But what is lacking is moving the dishes from the table to the dishwasher, to the cupboard, to the table. Your clothes from the hamper to the washer, folded, and put into closets. And then the trash cans need to be aggregated, the day of garbage night and put into the trash can moved to the curb, and then after it's picked up, brought back to, wherever the trash is located. But it's the logistical things. And you have a humanoid, where I think we're on the same page here. The end game is the humanoid form factor, because you're building a device that can navigate within your world and use your tools and that kind of thing.
Yeah, let's start walking through those. So I am the designated take the trash cans out to the curb and take them back every week at my house. This robot, this size, with this amount of strength, I don't think is capable of doing that. So this robot won't be able to take the trash cans out. taking the trash bag out of the kitchen trash, it should be able to do that as long as it's not too heavy and if you don't have a roommate like mine, which stuffs everything down for the sake of efficiency. Folding clothes, I specifically updated the geometry in my version of the hands so that the thumb can pinch to a point with the front or the rear finger. So I can pinch, or the hand can pinch. So it should be able to fold clothes. So some subset of loading the dishwasher, let's just assume the fingers are capacitive so that it can hit the touchscreen. Operate it, and put it into the bin and maybe take the bin somewhere. Those are a possibility.
I can see where the dishwasher just becomes the cupboard.
Yeah. So he should be able to load and unload the dishwasher. That's short enough for him. But all of my dishes are held high up, so he wouldn't be able to take the dishes out of the dishwasher and put them up. So
that's a stepping stool.
Gonna go high stakes. Okay. All right. Maybe with a stepping stool.
Yeah, I mean, I meant that seriously. Like a stepping stool.
I was going to ask about that, but then the whole idea came in is the balance.
So using tools, that's what, from a hardware platform standpoint, that is within the realm of possibility.
You mentioned that 4-foot kids could do all those jobs if they figure it out, right? Yeah. If
He knows
there's whole
he's put his-
algorithms for this stuff. I mean, you're folding laundry. That's a tough one.
Yeah, I was
You're
thinking
talking about like way beyond.
Well, the software. We're going to assume the software works.
Yeah, no, I'm saying that assumption is absolutely invalid. But we'll get there. But it's like we're not even
We've
close.
seen
that's massive.
Yeah, but we've seen the reinforcement.
PR2 can fold clothes.
Mobile project, right? It's already folding laundry.
I didn't know that.
Yeah, you bring up the video at some point if you want to show them Aloha Mobile. Alan's built a cheaper version of Aloha Mobile. It's just got 2 arms and, it's just stick figure and it can fold laundry given the latest research and demos of reinforcement learning.
My kids climbed up on the cabinets to put it in. Yeah. So you can do that too.
Yeah, climb up.
I'm okay. Speaking practically from a hardware platform, I don't know that the arms are strong enough to lift
maybe
the
not.
body up.
Maybe not.
But the stepping stool, yeah.
Imagine,
What's the next
3 kilograms,
Yeah, here, let's take a look at the sheet.
which is like a little under 7 pounds.
Oh, I was thinking that's like walking a small dog.
Mhm. That's what I was thinking. Maybe feeding the
What did it say,
cat.
3.2
Where
kilograms.
did we see it?
I think it said 3.2.
Yeah, I think it was on the pricing sheet. Maximum arm load, 2
Oh, 2
kilograms.
kilograms.
I'm going to assume that's combined, so 1 kilogram each arm, but I don't
Wow,
know
that's
that.
pretty light. Yeah.
Not much.
But if they
2.2
unlock the
pounds.
additional force, it's 3 kilograms. Maybe they do mean 3 kilograms per arm. What else? So Brian, to your point, my Alfie and the humanoids are both waiting for the same future series of software breakthroughs to make this possible. So about the same time that my Alfie can do this stuff, these guys will as well. So I'm going to put Alfie back together. He's going to join the stable of robots. I'm going to finish him once I finish with the hand and the forearm. But yeah,
Is Alfie your NVIDIA? Is Alfie your InMove?
No.
Alfie, yeah,
Aloha
Alfie,
Mobile.
my Aloha Mobile, my
Oh, the Aloha Mobile. Got it.
Aloha platform. There it's let me see if I can bring him up without crashing Fusion before I switch over. No, maybe not. So yeah, he's a low cost short robot that I built.
Yeah, I've seen that one. Thank you.
We talked about him during Ross. Yeah, that one, my Ross bot. Let's turn our attention to the current focus of my OCD, and that is the hands. Let me go ahead and switch this over to. Actually, I could just open it up this way.
The white and red are the little servos.
Those are the servos. Yep. Let me go ahead and open this up.
A bus servo, right?
Mm-hmm. All right, so my hand design is about 80% complete. Now, in the interest of time, I also modeled the original G1 hands, and I'll show you how I got the proportions. It's a really fun technique to do. So over, sorry, there's a menu off screen. So the OG hand. Here's what I wanted to bring up and show you. I have an old versus new hand comparison. So after spending a couple of weeks painstakingly recreating the factory G1 hand, which is all CNC milled parts, it's all custom. You can buy one of these hands for your own robot for $5,000 each. When I started pricing out like proto labs to get the components milled at even medium production quantities, it kind of makes sense. It's just expensive. Now, in order to do this, I did a couple of neat techniques that might come in handy on your Fusion journey. Oh, they also recently changed the name of Fusion 360 to Autodesk Fusion, in case you missed that. Here's what I did to get an accurate versions of the parts. I'm not working offline. You're offline. What's going on? And so how to do that is what I'll do is I'll create a new project, and then I will import the STL, which you get as part of the ERDF, the simulation file, as reference. So that's imported. You can't select any of the facets. It's not good for anything, but you can then use that to create drawings. And I've already moved everything over, so it doesn't line up anymore. To create drawings, and then to recreate that component using the drawings that you drew as reference. And so that's exactly what I did. And then after I did that, because the ERDF STL files are very simple, I looked at the videos and the photos to create additional detail based on what they suggested. And so once that's done, you can export the part, and then it's available to you to do other stuff. And that's exactly how I recreated from scratch every one of these parts, including the palm. So I had this for a little while. I was able to study it. It's fully jointed and articulated. And then I set about to create my version, not having these super slick and super small serial bus servos. These are 100% custom. I scoured AliExpress, Alibaba. No one else in the world has them. So you got to figure out something different. So what I did was I found the smallest Metal Gear serial bus servos I could find. And these are the SCS 2332s. They're amazing, but they don't fit into the same envelope. So I had to figure something out. And what I figured out was that if I ordered some, well, I got to drill down a little bit. I'm looking for this. If I ordered some 90-degree bevel gears from AliExpress,
Those the gold things.
and this is super exciting because ever since I was a kid, I would get Boston gear catalogs and I'd be like, oh my gosh, you can buy a machine gear for $40 or $20, right? These are $3.50 a pair. So I ordered a whole bunch of them from AliExpress. They got here in a week and a half. And that allowed me to take the rotational force required for the finger and move it off to the side. And then after that, I can just tilt the servo 5 degrees so that the tab sits within the envelope of the existing servo. And if I extend this by 4 millimeters and extend this by 2, everything fits. My brackets are also a little bit thicker. I'm using a carbon fiber infused PET G. And so check this out. I want to pass out 2 things. This is a 3mm bracket. These have not been. Here, we'll pass this one forward and pass this one over. I haven't cleaned them up or sanded them down yet. They're straight off the printer. But check out how stiff it is. So I found with a 3mm thick bracket, it's stiff enough for me to trust in a robot that has to do stuff and bump into stuff.
PETG is usually pretty flexible, isn't it?
Yeah, PETG is the same stuff in your water bottles. And so it's super flexible, which is great. When PETG was available as a printing filament, people started using it for drones, but it's so flexible that it messed with the dynamics. And they now make it available with chipped carbon fiber, which actually makes it super stiff. So you now have the super material that has a little bit of give, but is really stiff and durable. So
what infill did you use in that?
so for this one, because I'm using 50% infill.
Oh, 50%.
So I've got two fingers here. One I shaved off the tabs, and the other one I didn't. Now there is a lot of slop in the joint right now, and that's because when I assembled these, I couldn't find my Loctite. So the grub screw in the bevel gear is slowly working itself out.
This one, we put a little cover so you can see the gears.
Oh, here, yeah, let's go ahead and take this off. Take the cover off and then
this has the.
pass it around.
Wow, so you got this whole.
This is great. So I've got a good design. I've modified it for the required geometry of, take advantage of the materials. So some things are a little bit thicker. And when you compare the original to my version, just in profile, it is almost exactly the same.
But you said you offset the thumb though, so you can pinch the fingers.
Yeah, so I did give it a wider swing so that they can pinch. It took me a minute to figure out why would you even have this joint, and I'm like, oh, so it can pinch stuff. My version of the hand is only 4mm longer. And it looks like a lot here, but remember, it's very, very small. And because I'm reusing the same parts files for the thumb, it is about a centimeter longer, but I can't think of a reason to keep it short. And so it's all the same parts. So I've got almost the same design. It can grasp stuff. I even bought 2mm silicone adhesive sheets that I can cut to shape. I'm going to take each one of these pads and I'm going to create infusion cutout like on a little sheet, so I can set it on the silicone and then just cut out the exact shape I need, and so it'll be grippy. I was trying so hard to have like the hand and the palm finished to be able to show you a completed hand, but it just wasn't in the cards, and I'm like, wait a minute, this is supposed to be fun. Why am I rushing to get this done? Yeah. So these are prototypes. It doesn't really fit. But again, the material is super fun to work with. Something of this size, it can take a spill and a fall without breaking and deforming, which is something else to consider for a humanoid robot. Right. It's gonna fall. Yeah. It's gonna do something dumb. So it's an amazing material. Over the next couple of weeks, I should have the hand design finished. And I've also started working on the 2 degree of freedom forearm that allows it to twist in 2 dimensions. And with the twist at the base, it'll be a 3 degree of freedom, 3 degree of freedom wrist. So this one's about 40% done. I'm working on clearances and attachment points right now. The servos have been ordered, of course. So at the end of this exercise, minus whatever is required to get it to interface with the base of the forearm, which I just don't know, I will have designed and constructed a replacement 3 degree of freedom wrist and 7 degree of freedom hand that'll be a direct upgrade and replacement for the $16,000 robot that I can't afford and doesn't do anything.
And the $5,000.
Yeah. So this whole thing, they want $2,500 for the 2 degree of freedom wrist and $5,000 for each hand. So you're looking at $7,500.
You're saving $15,000.
And this whole thing, the bill of materials for it should be less than $400.
So now let me.
Yeah, these are $20 for each. Yeah.
Could this be used on your Aloha robot?
This is too big for my Alfie, but on any similar sized robot, you'd be welcome to use the design. It's super robust. There's another guy out there called the Robot Studio that is doing these really complicated, high degree of freedom hands. And he tried to use the cheaper versions of these servos, and he also built one with this version. And his firsthand experience is that these aluminum bodied serial bus servos, the aluminum body operates as a heat sink. So they just don't overheat. They heat slowly enough that when you do hit a critical temperature from forcing it beyond its limits, it's able to see that and shut down before burning out. Unlike the $7 plastic body version of these that tend to burn out a lot, they just heat up too quickly.
Hey, those little push rods, they look like they might be taking a lot of weight. Are you going to make those out of aluminum, or are you going to?
They're aluminum ends, and I think they're steel, but yeah, everything here is very small. I don't expect that to. The servos weigh far more than the rest of the assembly.
The push rods are parts that you can buy then?
Yeah.
Okay.
The push rods and there's threaded rod underneath. You
Oh,
can get it
gotcha.
from Amazon.
So you can adjust the length.
Yeah,
and
or if you want to
everything.
save a few bucks, AliExpress.
Yeah, okay, gotcha.
Just like the RC cars have these. tie
That's
rods.
exactly what these are for.
Yeah.
Yeah. Yeah, so probably about 2 weeks to finish the hand design, and then about 2 weeks to finish this. The servos should come in next week. But yeah, it's been a lot of fun. I don't want to say I'm obsessing over it, but I learned a lot more about fusion and multi-part design. And when getting back to the G1, now I've got to decide if this design aesthetic fits in with the rest of the robot, or if I want to update the design to include a vented cover out of carbon fiber PETG to kind of hide it. I'll probably doodle it this weekend to see if I think it looks better or not. But yeah, the hand's performant, it's strong.
I want to ask kind of a crazy question. So the hands have certain lengths, and when the robot moves its arm, does it have to know how far? Is it going to bash into stuff if the hands are too long? You see what I'm saying?
Yeah, the motion planner needs to, in order to be successful, programming this traditionally. Now, reinforcement learning is a whole different ballgame, right? But if you were to program a motion controller for your hand in your robot, you actually need to run a little simulator that is aware of the joint's position and location, as well as your joint position location of known objects, integrate LiDAR.
Yeah, that's right.
That's something that, yeah, you would definitely need to code for.
So you were going to do that in that, whatever that Omniverse or whatever that.
Yeah. And then under reinforcement learning, I don't even understand, like I understand how it works, but as they find more tasks and I expect that's just handled as part of the reinforcement learning motion planner, but I'm excited to see. But yeah, short answer long, if you're not careful and you're not paying attention to your surroundings, it's very easy to bump into stuff. Yeah.
Using a laser with its receiver and in modulation.
Yeah, it's funny you mention that because that's exactly what it does. It uses the front one uses an Intel RealSense with structured light, but in the head it has Mellanox. I don't know why they didn't use their own. And it's actually laser time of flight. And there's one motor that keeps it spinning this way and another motor that keeps it spinning this way. So it actually maps time of flight and laser the entire room.
But at the end of your finger, it's about the size of a nail. As you approach the object, it'll, indicate, there's an object there.
Oh yeah, the Ben actually gave me a little tiny board time of flight sensor. Yeah. So yeah, if you included those on the fingertips, it would give you some additional input as you approach objects or obstacles. Yeah.
I was going to ask, what were the original weight of the hands, like the ones that cost that?
I don't know if they provided that. Let me take a look.
One reason why I asked is, let's say you do proceed to get the $16,000 model. How would balance play a factor? Because I'm assuming these are being much lighter in the middle hands. I just don't know what balance would be.
Yeah, that's a really good point. Could you slap on my hands on the 16,000 and still have it perform? I think the cheater answer to that is no, but only because the cheapest version is radio controlled and didn't come with articulated hands. And I don't think that their radio control would support that because it wasn't available. But this is a lot of guesswork, right? As we wrap up, and I think you're going to go a little bit long. The last thing that's kind of bugging me about their approach is how many versions of the hardware they have. Now, I'll share with you the very specific reason this bugs me. Personally, I think they should have just released a $25,000 version of the bot with all the features and not have this segmentation, but this is their business model. They have a cheap version to get you excited, and then for all the fun stuff and the paywall, and they're actually planning to work on this. When you're working on your reinforcement model, so Isaac Jim or Mujoko, and you're training for these new behaviors, it's for a specific hardware configuration, right? So there is a lot of exciting research that's going on about transfer learning. Like, could there be a general humanoid robot base model that you could then fine tune on your specific robot? All answers, arrows point towards yes, right? That's one of the future directions that we're going. But when you're training a model to do tasks and you have 3 different hardware configurations, you have a base model with no wrist and no waist. You have an intermediate model with a 3 degree of freedom waist and a 2 degree of freedom wrist. And then you have a third one with all of that and articulated hands. You're going to be training 3 different versions of the model to do things. And that just seems really weird for me. I guess they're going to do it. They're kind of backfilling that into their business model. But one of the mistakes that they're doing right now is having 3 different specific hardware platforms with 3 different capabilities. Because any reinforcement learning solutioning they're going to do, they're going to have to train 3 different times, which seems a little bit silly. So a couple of weeks, I think, to finish off the forearm and the hand. I'm expecting to have that in hand, get it, next month to show off. And then, who knows, between now and next month, who knows what software features are going to be out there to face it forward. We've seen a lot of hints at what these should be capable of with the software we have available now, and that's only going to continue.
The other thing too is it says like, once you pay for the whole thing, you don't get it for like 6 months.
Yeah, I think
then how much advance would could you have missed out on something?
Yeah, so I'm going to skip the first production run for obvious reasons, and I don't want to spend the money. But yeah, it's happening quickly. And now that the G1's available for simulation, and there's excited nerds like me that are like, software, this is the first one to make the model available, and that, so the conversation can move forward very quickly as excited people like me take the available technology, new limits, and find new stuff. So you thought things were progressing fast now.
On your dog, he walks, but the Boston Dynamic dog, I went to a presentation on that. He has this articulating arm on the top of him. Is that an add-on for that Unitree over there, or?
Yeah, they do have it available. I think it's a robotics dynamixel arm.
Because it's just the dog walking. I guess he could be a security guard. He could walk around and look at things and identify it. But if you wanted him to do something like pick up some garbage or something, or
they do have a lower. They do have a.
Oh, what is that?
I'm afraid to ask. Let's see if I can find a quick pick. Yeah, they do have one available to it. It's $6,500. I think it's the upper capability dynamic soul.
It's more than the dog then, because the dog is $1,600, right?
Yeah, let me see if I can find.
I mean, it's great that he walks and jumps, but if you wanted him to actually open a door, that's where that arm comes in.
I can't remember where I saw the pricing sheet from it. It might not have been on there.
$20. Those are nice servers. My servers are like $3, my micro servers. Can they break?
Yeah, these are,
Yeah.
the ones in the hand are $20 and, first person, someone says, yeah, they're,
Oh, it's $2,800. I thought I saw something for 16.
oh, that's the go-to pro. That's the one that they want you to buy. The,
Okay, there we go. But
Yeah.
the Pro you think might have an arm?
the pro
Capable.
doesn't have it. I don't even know if the air supports the arm, but let's see if we can find it. Unitree go-to arm.
I mean, he could, that would be able to walk over rough ground and upstairs, you know, and it could go look at things. You can send it out, you hear a noise out in your yard. He would walk out in your yard and look around.
Here we go.
Not a he though. I said it. Oh, there we have
Oh,
something.
4,900. Yeah, that seems a bit much,
It does.
but
Yeah.
yeah.
But it does do something. There, it's got two fingers that pinches something. I can see it unfolds, right? Yeah, yeah. It's kind of like a scorpion arm or something. That looks awesome.
Yeah, just,
It could theoretically take a door handle and open it.
in theory, yeah, it should be strong enough.
Yeah,
And there's a rotate.
yeah, that does look cool. Oh, I wonder if there's a picture of with it on the dog.
Let's see.
There we go. Now we got a dog with rapid eyes.
Yeah, so it's got the Mellanox 3D LiDAR in addition to the one down here. It's got the 100 teraops Orin backpack, and then it's bolted.
That looks like the Boston Dynamics dog. Yeah.
Yeah. The only, and I like the Boston one better is because on that one the arm looks like a head, or the hand looks like a head.
Show them the.
I tried to write a use case for the company I use. They came over and I said, okay, here's what we can use it. It's $100,000, by the way. That's how much that thing costs, but it didn't get approved, so we didn't get it.
Show them the body with the
Covered.
Yeah.
They got a soft body for it. Yeah, there you go.
Oh, I didn't know you could put a costume on it. Well, there we go. Now let's save it.
This is an amazing use of the hardware platform. I don't know how it's going to stay cool because those motors need circulating air. So, but
by the way, those arms, when they pinch together, you lose your finger in that. You know, they gave a big long training session. You know, you can't. You got to keep your hands off. You know.
See if I can.
They look friendly right there, but they're actually they have pinch points for humans.
Yes, and when you get up close to fun, you'll see that they have hands away from.
There we go. That right there. Yeah.
So yeah, so that's all I've got for this month. It's been a lot of fun, and I'm hoping I can finish off the hand project so I can get back to putting Alfie back together.
Oh, your 3D renditions and 360 Fusion, you're so far ahead of me. I mean, that being able to rotate around and looking at that is really awesome.
Do you have any like intermediate use cases? Like if you have a wrist and a hand, now you can do pick and place or do something. Are you going to try something before you go full robot on it?
I might. My first vision was I would just set it up because I do want to play with control and I need to see it move.
Sure.
Right? But then I don't have anything robust enough to attach it to really.
You have the dog.
This is his excuse to buy the robot.
Yeah, they already have the hand.
Yeah.
Yeah, I am personally trying to trick myself with the slippery slope.
How else?
The sunk cost fallacy.
How else would you test the hands if you don't have the body to go with it?
Yeah. Yeah, because I do want to test load feedback and stuff, but yeah, to actually a manipulation test.
Do those servos have load feedback? Those $20 servos? They in the hands.
They have which?
Load feedback.
Yeah. Position, velocity, acceleration, and load.
Okay.
Load is kind of a parallel for force, but you have to take into account the fact that stiction and frictional losses mean that there's a minimum load that makes sense because and that would be velocity.
But you can tell it to squeeze something not too hard. So
you can set a load
it wouldn't
limit.
break this servo.
Yeah.
Really is what it comes
Yeah,
down.
which is one of my game plans for Alfie and for the G1 I'm not going to buy is all of the shake hand demos, including the one that they have coded.
Squish someone's hand.
That's just it. It's their shake hand demo is they stick out a hand and then they bring it back. It's completely passive dead fish and it bugs me. So for Alfie, if I can get that far for the shake hand, I want it to be smart enough to know when someone's grabbed it because there's sensory feedback to say when that's happened. And I want to be able to close the hand with the minimum load so that it's actually holding you. And I want Alfie to move up and down. I don't want to rely on the person to do it. You know, small victories, small things. But yeah, it's hopefully the minimum load is low enough to not panic people when the clock closes.
That's a little scary.
That is actually hilarious.
Gotta have compliance.
Right, yeah, maybe incorporate some springs or something, yeah.
Compliance detection. So it's working with humans. You gotta have it.
Squishes their hand out.
All right, so yeah, thanks everyone.
Thank you. Next, Jim, you will be taking over.
Yeah, I'll do an impromptu coverage of what I've been working on, which is my Truckasaurus robot with GPS capabilities. Let's see, host.
Yeah, Jim, if you turn on your camera, I can spotlight you.
Top of the truck. That's a little laser that's.
Yeah, I'm gonna have to put some decoration with the real Simpsons Truckasaurus insignia on there at some point. Oh, I can use there. First, I'd like to just show some. First I want to show you the. I was going to do this in show and tell, but I have a video of the latest work I did prior to doing GPS, which is the first project was to get the Truckasaurus navigating using LiDAR and around the house. So I wanted to allow it to use, or get it to be able to use the standard navigation stack for ROS. Having trouble here getting the window to, let's try to, or wait, I need to share with video. Let's try that again. Share screen, sound, and video. Now, it seemed to
Something about squeezing your into, and it's just killing me.
I am not
shaking.
We watched the Cybertruck videos where everyone's closing the trunk or whatever, chopping up carrots and fingers and things.
Yeah, the Model Y had the same problem. Or no, not the Model Y, yeah. The X with the building doors.
Oh,
and
those are scary.
Yeah.
What's the problem with Model X?
The goalies, they smash your heads.
Oh, I didn't know that. The articulating doors. Yeah. I didn't know they did that. I mean, I didn't know they squished people's hands. Because they shut automatically. Yeah, that's what. The back doors in the Model X, they open. Straight up. Which is handy if you don't have a lot of space, so they don't swing into something. Yeah, you don't put your hand in place. But even the even Hondas, check this slide. So he's trying to use his truck competition that was colors.
Oh yeah, the Firefox is not behaving very well.
Yeah.
Let's see. So let me show you the. I've shown some of these videos already. So this one is the latest.
Let's try this one more time.
And what I've done so far with the navigating around the house.
I've increased.
And what is all that? This is black stuff here.
A little bit.
Yeah.
Because
Yeah, laser. So that's what I'm talking about.
Get this out of the way.
It was bumping into things.
He was talking about that. Humanoid also has a little sense. Usually. What's this?
Yes, I'm sharing the whole share.
You want to stop and restart your share to see if it goes away? I don't know what that was.
Sharing the entire desktop.
That's good.
Which is, they like to hide things. Like it's.
How does that pop up?
That was. Okay, so
See what it does here.
So this is the navigation stack and ROS, and my robot indoors. And this map was created with just the LiDAR here. It's a SlamTech mapper. And so what I did was I created I clicked on the map and set some waypoints ahead of time and saved those. And now I run a script a Python script that tells the robot to go to each of these waypoints and wait for a few seconds at each waypoint and then continue on. So this is a culmination of, and you can see it.
So that's the first stopping point.
I've had to, you can see it navigate through doorways and a little bit tightly because I had to change the pad. It's sort of a padding or the inflation, they call it inflation map.
Inflation layer.
Inflation layer pads the wall.
Great map, Jim.
Yeah. And so in a house like this where things are tight, you got to reduce the padding, the inflation layer, so that it can reasonably get around. Because if it in ROS, basically, if it gets stuck in one of those padded in that area between the wall and where it thinks this inflation is, the robot will get stuck and not move, even though it could move. It just thinks it can't move. So I had to reduce that to a certain point, and it's like sort of a bit trial and error. This is a run where I'm showing you kind of the walking with the map, viewing it on the computer, and then I have another video that just shows the robot going. So this is the challenge here was, getting an Ackerman-based robot to navigate, and it requires a bit more agility, some backing up, and in a tight space like this, it's not as good as a differential steering robot or differential drive like Orange or other robots that have the two wheels and not Ackerman. But with the sort of persistence and patience and adjusting the parameters, you can get it to work. Now it's in the file. This is using what's called the MPPI controller.
I can see you walking behind it.
Yeah, you can see me walking.
All right. Now it's finishing.
So you have to select in ROS navigation. You have a long-term planner and a local planner, and this one is, and you have to choose from a list that are available or write your own controller. So this one called MPPI will handle Ackerman-based steering, and that one turned out to be that's the local one, and the global planner. I forget what I'm using also one of the choices, but and here's what's that?
Like SMAC or something?
Yeah, the SMAC controller. Now, this may not mean much to you right now, but so that you can choose these different controllers, and some of them are compatible with Ackerman-based robots, some of them are not. And I had to choose a combination that worked the best with this basic. And some of them are fairly bleeding edge, the MPPI, and I had to recompile the MPPI controller because it kept crashing. The binary distribution. So here, why don't we listen to what I'm saying? Maybe this is more prepared.
Hello. Today I'm going to demonstrate Truckasaurus doing a run around the house through some waypoints that I've set up and saved, and I'll be running a script that sends them to the nav2 waypoint follower. Alright, so I'm going to show you how I started up. I start up the micro ROS, and this is Lino Robot 2 hardware. So it starts up the micro ROS and the teensy, and subscribing to all the topics it needs to. This one doesn't have real encoding
Starts up
currently, but
the
it
base
probably will do that. And then I launch nav2.
Then you have to launch the nav2 stack separately.
And that is bringing up all the navigation stuff, except I don't use AMCL because I have the SlamTech. My SlamTech LiDAR mapper produces a pose for me.
So you don't,
and then
AMCL would
the next thing I have to do is
using this algorithm,
load the map.
Algorithm for probability of where your robot really is based on the sensors. With the SlamTech mapper,
so
it has that probably built in. So I can just use the pose.
Set map.
That uploads that processing. I don't have to run this extra node. And then I'm loading a map.
That loads a map file that I previously saved. Now I also will do a set map.
And then you can turn on update on or off, which will mean that if you want the map to stay static or you want it to
because it defaults to
false, close the door, or move a piece of furniture.
Just do that a few times. And the map might have
always
some crud in it somewhere.
That's the local planner will.
Don't want that to affect things.
Obstacles.
The robot will wait 2 seconds after each waypoint, as I've instructed
the Python script I was telling you about.
This pause
that you run, that I'm running, and there's already a waypoint follower module in ROS. All these are modules that you can load, and you give it a list. This one, it kind of, again, I had to make the inflation so close that it's to the error can send it into the wall, like Alan says. Well, this is obvious. This one, actually.
I've tightened the.
Back up just a little bit.
The problem.
Surprising.
The problem is it's done this twice now. Like I ran it the other day or yesterday, and it also clipped the wall. And I'm not really, again, it's like the inflation is trying to keep it away, but there's some degree of error because my RPMs of the car, the steering, not everything is perfectly synced to the theory of what is sending the robot. So that's why you have inflation layers, because you need a buffer, because you don't know where the robot really is in real life exactly at all times. And but I don't want it to get stuck either in this like inflation hell where it just doesn't move anymore. So I have to cut it close, and sometimes this is going to happen. You have to tweak things to get things more and more accurate. My throttle model isn't perfect, so it doesn't go exactly at the RPM it's telling it to, and all sorts of things like that.
I've tightened
there's like
the padding, so it's not much padding because it's kind of tight in this house.
So the thing that kills the critical.
Yeah, that was its waypoint. Now we go to the next one.
Further away, but it's okay right on top of it.
Yeah, there might be. I have, there's so many parameters. I just want to spend, forever working with this because this robot is not designed for indoor use. So this is sort of a proof of concept.
Waypoint. Moving on.
Proof of concept that to test out the whole navigation system what I had ready, which was the mapper. So that's the whole point of this, is replacing it later with LiDAR, with a GPS. I
There's a
can show you
waypoint.
that as well, or what I've gotten so far. But this whole effort was to get a rough system to test out
Two
a
seconds.
navigation
No.
with just the LiDAR or mapper in indoor situations. But that's not the
The
goal of it.
final waypoint.
Not going to use it indoors, so this whole effort didn't have to go too perfect. I don't have to work on this anymore
That should
because
be
it's
it.
just to prove all the other systems.
Okay, let's try this one more time with the to show you the
Point is,
how it
I want to
plans the
get
path.
GPS anywhere if it works.
I've increased it's first amount of
Okay,
distance.
So you've seen this now. So that, any questions on that so far? That's where I got the thank you.
Looking good.
That's awesome, Jim. I know a lot of work went into that.
Yeah, thanks. That was a bit of effort. I kind of went that route, without kind of giving up the idea of, or not pursuing the outdoor portion yet, because I was just wanted to get all of this working and prove that it could use the mapper and navigate in a reasonable way with around walls, and hoping that the mapper would work outdoors to some degree. I'm finding now that maybe not. I'll just be turning off the LiDAR, or for outdoor, unless I find I'm still experimenting with it. But it just using the odometry of the actual robot might be good and better than that LiDAR, because outdoors there isn't enough for it to bounce off of. Yes.
You modulate the signal. You can get rid of the standing color, sunlight or whatever.
Yeah, well, this one is designed to work. It works okay outdoors without direct sunlight, but it's designed for, reasonable outdoor use already.
So it probably is.
Maybe it's modular. Now, this is a time of flight sensor. It's not the triangulation. Which was like one of the earlier time of flight LiDARs that Slamtech made, and they put it into this package of a mapper. So it does better than your triangulation style, which has the eye, if you look at the separation of the two eyes on this, the receiver and the transmitter, they're very close, and that's a sign of a time of flight sensor, whereas the other ones, like the A3, A4, those different triangulation ones, you'll see the little holes in the very edge, at either edge of the LiDAR.
The NITO's a triangulation.
Yeah, so luckily this one, yeah, does have a work. It was designed to, go outside. It will be limited by direct sunlight. That can kill it. But I haven't really got to it's of limited use, but it can still work outdoors. Now the other, okay, what I wanted to show here is, okay, yeah, let's zoom in to my different. So I want to point out Automatic Addison, give a shout out to his website and tutorials. If you want a lighter introduction to a lot of these ROS concepts, a bit higher than beginner, but lighter than the ROS documentation, then the Automatic Addison, he's a gentleman that has produced a whole bunch of wonderful tutorials and via these like posts. And he references the real ROS, or the official ROS documentation as well. But I've emailed him. Maybe he could be a future speaker. I don't know. He is a consultant. You can pay him money to help you with ROS projects. But I'll see if I can approach him for a freebie for us. But yeah, so there's all these different ones, including tutorials involving GPS and navigation and step-by-step. Some of it might be older versions of ROS, but I definitely recommend that, and I'll paste this in the chat. There's just a bunch of different tutorials he has that are really good. I don't know, where's the chat? Chat. Here we go. Paste it here. So let me show you. Truckasaurus rocks. Thank you. A lot of this gets kind of there's a lot of detail to the navigation, but what I do have is some let's see, some diagrams. Yeah, so this one, so integrating GPS data. Now, Automatic Addison has a nice tutorial on that, which is here, how to use GPS with your robot. And I've been working on this a while now, over the past month, I guess. And let me go down to that takes some time to go through, but what I want to show you is kind of, well, here's a nice diagram of, your robot has its different frames, and it's got a local frame and it's going to have a global frame based on the map. And so with ROS, you have these different frames, and there's also a tutorial about those frames in Automatic Addison on another one of his tutorials. But essentially, you have a local frame, which is your local coordinate system of your robot, and then you're going to have a map frame. And the map frame, in this case, for outdoor use, is going to be GPS based. Indoor use, it's based on your LiDAR map, right? Your map that you create, like you saw with the previous demo there. That's a map made from your LiDAR, and that gives you this map to odometry, or that will create a frame, a map frame, and your robot will also have an odometry frame. So these two frames will shift. There's these two frames, and they will shift because of accumulating error in your odometry or the map. But this is a critical part of ROS, where you have a map that's being created by LiDAR or GPS, for instance, and then you have your odometry of your car that's coming from its sensor on board, and that is a separate frame as well. And through special node called the EKF, or a localizer, it takes these disparate pieces of information, and through statistics, essentially, it figures out the best fusion of them.
Oh, so it doesn't say the map is always right. It doesn't true up the geometry to the map. That's
right. It's a fusion, and that's based on, this is the robot localization here. It's a fusion based on statistics. So you have a thing called covariance. Covariance is related to standard deviation. So if you're familiar with statistics, oh, well, the sensor is accurate to plus or minus some number of angle degrees or some number of centimeters. That can be converted to a covariance. And a covariance matrix is what ROS uses. And these things called the EKF, or robot localization module, and we'll take that in. So you need to kind of know what is the relative accuracy of your sensor. You have to try to find that somewhere by the manufacturer, or you could do your own testing of it if you're so inclined. And it's one of the hard things I've had to try to figure out to get some numbers. I ended up just copying from, I don't have real, realistic actual numbers from the sensors or from the, the LiDAR. So I kind of copied, but essentially they're small numbers. They just can't be zero. Zero would mean your sensor is 100% accurate. And that is a very bad thing to put into a localizer, into a extended Kalman filter, which is what EKF is. It's trying to fuse these different pieces of information. And if you tell them they're both 100% accurate, it's not really true. And therefore it's going to start, because the real data coming in is not accurate, it's going to start ballooning the error. And you don't, so this is a very important part of this, is that kind of error estimation that you need to find out. Okay, so GPS is what I've been involved with now. And luckily in the ROS world, they have a whole GPS effort that's been going on. And based on your standard GPS coordinate system, this WGS84, they have node that will convert the GPS coordinates to your local coordinates. And that's through this thing called navsat transform. And this is some background on how the GPS system is being used by your robot, by a projection plane on the surface of the Earth. And because the standard coordinates of GPS are like a radius to the center of the Earth, and it's just not a practical way to use latitude and longitude or this other system. It's just not practical in a robot on the surface of the Earth that needs to go like 20 meters or 100 meters. You want it to be on this projected plane, on a flat plane. And so that's what this conversion does. And then it will map that into your robot's local space. And so this is a whole tutorial you can go through that will use Gazebo, and you don't need any robot or anything. You can run this tutorial and see how this is a fake generated GPS coordinates from a simulated sensor, but at a real location in the world on this racetrack. Right here, you can see this racetrack. And so I'm starting to use this system in the real world now. And that's how I'm trying to navigate the robot and be able to have it go from waypoint to waypoint in GPS coordinates. And there is a new waypoint follower that's available, but it's only in iron, the latest short-term ROS version called iron, which is actually going to be retiring in the fall and being switched to another one. But there is a new long-term one. But currently I'm on Humble, which doesn't have this feature. So I may want to upgrade just to get access to this interactive GPS waypoint follower, which is kind of exactly what I want, rather than writing my own. I don't know how much code is involved here, because it seems like I have all the elements to generate, to convert GPS to your local coordinates with that navsat follower or the navsat transform. But it's always good to take advantage of these nodes that are already been written in ROS for you, and they're in different stages of development. So you may have to upgrade, but it may be well worth it. So I'll get back to you on that. Let's see what else. That's the.
So you haven't moved to iron yet?
No, I didn't move to iron. I started with Humble.
Yeah.
And maybe I'll ask this crowd, you know, how much effort is it to upgrade it I guess my code, all the code may not have to change at all because the difference between Humble, Iron, and even the new one, the new
Jazzy.
Jazzy?
Jazzy Gillespie.
There,
Gillespie.
Jazzy, there wasn't a big change in API as what you guys have told me, as you know, compared with the previous long-term one. So maybe it's just beats recompiling, you know, rebuilding the whole thing.
I would probably skip Iron.
You might be able to run it on a different workspace.
Jazzy's been released already.
So what's really cool is when you have a particular version of ROS that's the short term, like Iron, they have short term and the long term support. So if it's something that was implemented in Iron, for instance, that I don't have because I'm in Humble, all the features of the short term go into the next long term. So the next long term one called Jazzy is now out. And so if I go from Humble to Jazzy, I should inherit all the new features that were added, correct? So from what I hear.
Yeah. And it's like, as I understand, you could do two different workspaces, but Humble's on Ubuntu 22.04 and Jazzy, as I understand it, takes 24.04. So you'd have to update your OS too.
That's the one thing I didn't want to do is upgrade my OS if possible, because that's a bigger job. So with that's one caveat. You know, this is a pain with ROS that affects everybody. Is they have the short-term version, a long-term version, and then when sometimes they change the operating system version when you go to a new long-term. And that's a lot more work for you potentially because you have to reinstall your OS. And
good thing is Jazzy is good to 2029.
Yeah, then if it, you know, once you upgrade, you're good for a few years, and that means it'll stay on that operating system and not upgrade.
Hey Jim, I know you're talking about GPS.
Oh yeah.
You guys want to see what a $10,000 GPS looks like?
Wow.
Here's one right here.
The stick and
That's
destiny,
base station, right?
Yeah, so you take this to like construction sites. So we use it on campus to map out mostly utilities like pipes, underground pipes. So when they're putting a new pipe or repairing an old pipe, we go there and then we stick it right on top of the pipe. There's even a leveler here that you can kind of level exactly. And it does depth and it goes up to a few centimeters.
So that's a surveyor grade.
Yes, yeah, exactly.
Is that a Trimble?
It is, yes.
Okay,
Yeah,
there we
this
go.
is the gold, the Aero Gold, which is 10 grand for this thing. But
Can we get the camera on that?
Acquire centimeter accuracy, like 10 minutes or?
no, it's very fast.
Oh, really?
Oh, yeah. Very, very fast. And so we have an app and we just point it and then it records the point exactly.
Do you just use the one or do you have a separate fixed base station that compares
No,
to?
this is it and then an iPad that we attach to it and then the iPad.
Can you get the camera on that?
Oh,
So we set up remote testing.
I don't know if you can see it or not, but
Let me turn off my.
kind of put it in front of Jim.
That is awesome.
Yeah, Walter's smartphone just released a new one. It's kind of like it.
Look out. Like Marco's gonna
Right,
whop somebody.
Yeah, you know, the entry for the
Uh-huh.
direction thing.
Yeah, I know, because some of those GPS, like the ones here, some of them are like $30 even.
Yeah, they're very cheap.
Yeah.
So I'm using Adafruit Ultimate GPS.
Oh, Adafruit.
Yeah, it's a little board, and
Yeah.
And then I added a external antenna.
What do you interface it to?
So that's USB. I'm using USB
Yeah.
serial. So I'll show you a little bit.
Adafruit.
So if I can, how do I get this?
A lot of GPS products, and one of the founders is really loves it.
So here, I've got these different scripts, and what and so I'm running ROS on this. The robot is actually running here. So
Ubuntu, I like that.
yes, we have to.
Yeah, it can't receive in here, can it?
Well, let's find out actually. Yeah, Gandalf staff.
you have package and then the executable. Oh, yeah, ROS 2 launch.
Yeah, so here, I'm using this thing called the NMIA navset driver. So what using serial. So if you have a GPS module, you can use a nice driver called the NMIA navset driver. Most GPSs talk with this a standard communication protocol, and you can even view it. It's in text with a viewer, and so this particular driver knows how to talk, and you just set up a serial connection. This is connected to the Raspberry Pi via a USB, and this driver that you can install knows how to communicate the protocol I'm talking about over to the GPS, and as a result, it publishes, and I'll just
Right, we have a lot of data.
it publishes information. So what we can do is, I'll show you here, RTL is my list. So these are the different things it publishes. And actually you can see it if I bring up RQT graph as well. Let me show this. You'll see the navset driver produces, I don't use this velocity, but in heading and the fix. So the fix is going to publish where you are, where the coordinates in GPS coordinates, or in that coordinate system with latitude, longitude. And so if you look at, try to look at, let's see if it's seeing any, it probably won't see anything here, but we'll see what it says. If it gets nothing, it'll just say like, not a number, or it won't publish at all. Probably won't work indoors. It does work if you're near, in your house, if you're fairly near a window, and not sort of deep in a building. And so I find that I get a little bit of, it will work. But yeah, it looks like, yeah, but these different, so what happens is it will publish the information there. And after lunch, I can do a demo outside. I'm going to try to ask Brian for some help, because I think one problem I'm having is that my GPS may not be publishing quick enough, the frequency. And so without having a fast enough publishing, then the robot's moving and it didn't get an update, and then it's sort of way behind where it's way ahead of where it is, or behind or ahead, however you look at it. But
how fast is your GPS publishing?
I don't know actually. It depends on if you're, but I think outdoors it's like intermittently not working well. And I have some questions about, like, is my antenna and all of this wire that's coiled up, is that a problem? This is supposed to be a powered antenna, 3-volt powered boosted antenna, and the old, so I have some questions about that, but we take it outside here, but it was not publishing very fast. It was really kind of slow.
Mine's publishing 1/1, so that's
1 time per second. Yeah, mine was like getting low. It was like intermittently low, less than one, or I mean, less than 1 second, or less than one. So
how's the heading expressed?
I think that's in an orientation, but I'm not using that heading. Let me run the.
Is it like 0, 90, 180, 360, or 340?
I forget what heading actually looks like, but
it's a quaternion.
It's a quaternion, yeah, I think. What is it going to do here? Let me run. Yeah, so you do have running these things in quaternions, which is 4-dimensional 3D space, and it's kind of I have a converter usually to help me with that. Now, I was going to show the compass. So I have it's very important to have a compass working, And so, let's see, I'm on let me launch this. You need a compass, and so I had to calibrate my, I had to do some work to get the compass calibrated. Right, this is Truckasaurus. So if I do, what do I got running here? Okay, that's the same. So if I run my main micro ROS, and this is the bring up, essentially the bring up script for the robot itself, which runs it runs several things. The micro ROS agent, it connects to the agent runs on my on the Raspberry Pi, and then it connects to the microcontroller running the motors and all that, and and also the LiDAR. So that's all this stuff gets run. You sort of connect from your Raspberry Pi to the microcontroller, and then you end up getting a bunch more topics being published, all these ones. And if I refresh here, you'll see there's a lot more. The Slamware stuff is all running here, which most of this you can ignore, but a very interesting, or most important, is the Slam Tech is publishing ODOM unfiltered, that's the pose of the robot in the map. And then, like I was telling you about EKF filters, so this is what happens. You get unfiltered odometry, which could come from your wheel odometry as well. That's what that's what you normally would use. And then the IMU data as well. And then, oh, I'm sorry, I didn't run the GPS one. I guess I should do that instead. So let's kill this one. So that, yeah, this L-Truck GPS is my newer script, which runs, so I have two versions now, one for indoor use and one for outdoor use. The indoor use one, is differently configured than the outdoor one with the GPS. And you can see because I don't need a compass indoors, for instance, right? It's not necessary. So now if I refresh this, you'll see a different set going on here. Now, the magnetometer is your compass, okay? So the compass has to be calibrated. So then actually compasses are notorious for having, I'm using what's called the 9250. It's an IMU, 9-degree of freedom, accelerometer, gyroscope, and a magnetometer, right? So you have these relatively inexpensive boards. That one is actually connected to the Teensy, and that talks over this serial, or actually, yeah. Anyway, that so the compass or the IMU needs to be calibrated. So at boot up, in the firmware, there's code that will hold while it's sitting still. It looks at the gyroscope and the accelerometer, and it takes a few seconds of data and then says, okay, well, we're obviously not moving now, but this thing has got some noise, so it sets a baseline. And for the compass, though, it's a longer calibration, which you only do sort of manually and drive the robot in a circle. So I drove it in a circle at home with the engines on and everything. And then I collected data, and now I have some scripts I can, by running this calibration script, I can, I don't really get this to it. Okay. I can either run a calibration and do it now and outdoors or whatever. Indoors works too with the compass. Or if I have a set calibration, I just run my script and it uploads. The thing about compasses is when you just look at the raw information, which is what this thing called IMU data raw, if you don't calibrate that information, you won't even get a full 360 degrees out of your compass. So you have to calibrate, and what happens is you end up getting what's called a scale and a bias for your compass. So the scale could be quite a big number. They could be quite a big number, like this, or the bias can be fairly big, and the scale can be big. So it has to. You drive it in a circle several times, and it's doing this calibration, seeing like, well, if you drove a full circle, it assumes you're driving a full circle at least once or twice, and then it's looking at the information and saying, well, the compass only reported, this small change, so that means that's the whole 360 degrees. So you have to multiply by a scale factor. And so that's what that calibration figures out, the scale factor. It takes like 15 seconds. You drive it around. It also calculates a bias, which is just an offset number. So those two things are kind of critical to get your compass working. And then at that point, like if I look at the compass now, I can say RTE, IMU, data. We can just use the raw. And then we can grep the orientation. And then I like doing this because it makes it a little bit easier. -A for. And yeah, that's not showing anything. Let's see. Let's see if we're getting any IMU data. Oh, there it is. Orientation, there it is. So initially you get like you get the magnetic information out of the compass, and then it has to be converted to an angle. But and then let's see, that's the data. So data raw is what's coming out of the compass directly. This is saying zeros, or I'm sorry. Acceleration, angular velocity, IMU link. Yes. So you have an IMU, you published, but that's IMU link. That's where it is. Yeah, so this is the information of the in quaternions, which is not a real friendly format. So I have written a script to show the heading.
What is coordinate W?
That's the fourth coordinate of the quaternion, which is it's a 4-dimensional space.
So is it time?
No, it's not time. It's again, like if you want to see the calculation.
I mean, I'll look it up on my own, but
it's a complicated thing, but basically you can divide everything by that W to get. It's like a homogeneous. I think it's homogeneous. But it's 4-dimensional space, so it's not. There's a bunch of equations with trigonometry to convert.
So are the X, Y, and Z the normal X, Y, and Z rectangular coordinates?
Yeah, so they're pretty complicated, and
it's complicated.
Like a roll pitch yaw or something like that, like coordinate. But they solve the problem of like gimbal lock, where when you're close to north, things get all screwy. So it solves those kind of problems.
Yeah, we don't have to.
Yeah. By putting in a lot of complexity.
Okay, I'll look it up.
Yeah, that's beyond the scope of this right now. It's like you don't actually need to understand quaternions to do the work I'm doing. you can just you can run you can get a little piece of code that converts them to Euler angles, or back if you want. But I'm not, it's a deeper question to do that, to understand all that. But so here you can see I've converted to degrees, and I'm probing from a few different sources, the magnetometer and the IMU as well. And so if we turn, let's see the numbers change here.
If they changed.
Yeah, so they're changing. So that's the compass is working there.
Are you just picking up the robot and moving it around now?
Yeah, so I just moving the robot to face a different direction. And I'm printing out different, the angles at different stages in the pipeline. I guess I should go back to, I'm sorry, this is an unprepared talk, but there's a lot of stuff, interesting stuff here. But rather than try to see if it's all working right, I can show you how the system is formed, which is you have an IMU is this box here. The raw data from the IMU, it is already calibrated by in the firmware. So the firmware has that scale and bias that I set, and so it outputs a calibrated compass reading and accelerometer and gyroscope. That gets fed into, there's a thing you can use called the Madwick filter. This is commonly used for pilots and all AHRS, if you've heard of that. But it's used to fuse the information coming from a compass and coming from a gyroscope and accelerometer, and it uses all that information to produce a more stable version of the compass of the IMU data. And this is a commonly used filter. Again, you can read a whole bunch of stuff about it, but it's commonly used for drones and especially flying robots, etc. But I figured it's useful here because it's taking in the raw data from my IMU and the compass, and it outputs a better quality version of that, right? And then that data, the IMU data, then is used by the other components. And now you'll see that we have two filters here for EKF. One is for global and one is for local. And this is a setup, a common setup that is suggested by the ROS community, where you have one filter just taking in the local things like your odometry from your robot and your IMU from your robot, and then producing an ODOM output, which is, again, it's a filtered version of the pose and orientation of your robot from this initial information coming. And again, the EKF, you can configure that to take very choice data. You can choose exactly which data it's taking from the IMU and the ODOM. For instance, X, Y, there's a 15-dimensional space, of parameters, including position, orientation, and acceleration and velocity. So basically, twist and pose are the big ones. So you can choose which things go to that filter from each of the sensors. So you can say, well, my sensor doesn't do velocity, or it doesn't do position, it only does velocity, or vice versa. And you configure the parameters. But in this situation, with GPS, we have another node, another EKF. That one is taking in more information. It's taking in the IMU data. Oh, did I not run I don't see, there's fix. It should be the EKF filter, right. If you go down here, you can see the EKF filter for the map is taking in the GPS. odometry. So this filter is giving you a global, outputting a global odometry, essentially. That's what it's for. So that's, see this odom global? So that one includes the GPS world location, whereas this odom is just in your local space, in your local robot's space. So that's its own coordinate system, like in meter, or it only knows its local world. Like I started 0, and I'm now 20 meters away from my 0, where I started. Whereas this global one, the global odometry, is now fused in with the GPS coordinates. So that so with these two different filters, you now have like a global and a local optimization filtering of both your global and your local coordinates. And ultimately, it goes to this thing called the nav. The navset transform is what can convert GPS coordinates that are from this thing called fix into coordinates that into your local space. So that's when you see this navset transform outputting odometry GPS. This is in fact in the coordinates of your. It's in the same scale and it's in the same coordinate system as your robot, but it's converted from the global, from GPS. So the whole point of this is so that you can have a robot that's located at a particular latitude, longitude, and you can still say go to this latitude, longitude, and it computes that, oh, that new latitude, longitude is 40 meters away. So then this so it can just say go to 40 meters or wherever that XY is in 40 meters away, and it's in that local coordinate system, but it's converted from GPS, if you get what I mean. So it'll convert to coordinates that your robot can actually turn into wheel movement to 40 meters away at this new XY, instead of trying to figure out where that GPS coordinate latitude longitude is. So anyway, I guess we're hitting, it's 12 o'clock. So I'll stop and we'll probably take this outside after lunch, and so I can get a real just try to get a real GPS signal. And I guess I could leave you with what I end up running is this thing called nav, is the map viz. I call it viz map. It may not.
Not gonna look at a GPS.
Yeah, it's not going to work. But this just to show you, for the people that aren't going to be here after lunch, this will fill in with a map of where you are, like a map, like it's on the wall there, over a Bing. It's a Bing satellite view, and it's very similar to RViz, except it's for mapping with GPS. It's like an RViz, except it's for maps, and so I'll show that after. But so yeah, so that's all for now. And if anybody has any questions, there's a plug for the university.
Well, thank you, Jim.
All right, Jim, let's go.
All right, so we are now in the show and tell. So far, I have Ellen and Jim. If anybody else has a show and tell, let me know so I can add you to the list. Those online.
I can show a short video demo.
I'll add you after Jim.
Well, I kind of did mine during the talk, so.
Okay, so I want me to take you off the. You're after Alan.
All right, so if someone could join on your phone, so we're going to take the bot outside and take a look, so that way our folks online can see it.
You want to do it before lunch? Or?
Oh yeah, show and tell before lunch. People don't have to wait.
Oh, okay, you mean, yeah.
Yeah, so someone could join the meeting on their phone. I'm going to mute. the meeting in here, so there's no crosstalk, and then we'll take this party in the hallway for a few minutes.
No, that's your phone, yeah.
Okay, yeah.
Oh, really? Wow. Yeah, oh, yeah.
So Brandon, do you want to be in the photo?
Yeah.
What's that?
Kind of looking at that. I'm getting more into the DS and stuff.
Okay. This is the go-to straight from the factory. It's the cheap radio controlled version. It is absolutely hackable. I just haven't gotten to it yet. So there's an app for that. So there's an app that you can download to your phone that gives you the LiDAR view as well as the camera view. And,
so it has camera too.
LiDAR.
Can I see the screen? Okay.
Yeah, so it's got two joysticks on. One joystick is forward, back, left, and right. And the other joystick is turn. And so it's kind of like running a so it's running the 8-year-old MIT sheet of code. You can see now why I'm making it snowy. The new AI mode is eerily natural. So in theory, it's not running into a wall. So the obstacle avoidance is on by default, which is great. Occasionally, there will be some contamination on the LiDAR. And it will give you a warning on the app, and then it just won't move. It thinks there's something in front of it. So you can turn that off if you need to. There are a couple of different tricks that are built into it that are kind of fun. Shake hands.
Whoa.
That's where you put the hands on there, Alan.
Oh. Can you repeat that, Cam?
I say there's where you put the hands on him.
Oh, Camp is asking something. Go ahead, Camp.
I'm saying you could put the hands on him when he's on his hind legs.
Oh, right, like
put your hands on him. Yeah, that would put your robot hands on him. That would look extra creepy.
Yeah, in the AI mode, it is able to handstand, so it's halfway there. So it counts and the robot platform itself is pretty performant.
So you'd have to put the hands on the feet, right?
Right. There's a couple. Can you do like a
dance and rock, whatever. Stuff.
All right, so like those robots, actually, I'm sorry, I'm not putting it in there, because left over because I'm standing in front of it. But it shouldn't. There's a few little dance routines that it's supposed to do. So what exciting for me about this, now you have access to the full API, and so you can write program and code that accesses the camera and the LiDAR. And you don't even have to do a full reinforcement learning model. You can still control it at a high level and do interesting things. And you can do that using the traditional sport mode API, it's the traditional controller, or with the new AI mode API. That's not available in the app because they have it paywall. But if it's hacked, you can switch directly over to it. So this is what's getting me excited about Magellan. I think it should really need performance. Definitely don't have to worry about traction. It's just a matter of writing the code to identify, localize, and touch a phone without knocking it over. You know, that little thing.
Well, he can do that little hand thing to touch the cone.
Yeah, you just touch it, reach on the paw.
Yeah, that was actually my goal, is to kind of walk up to the cone, and then if I can get it in just the right position. Oh, wait, no, wrong button. Follow the person the right button.
Stretching us back there.
Yeah, there you go.
That is so cool.
Yeah, my dog racing.
I love to that. I'll take that in my hand. Take that straight. Everybody watch your back. Just walk into a dog and jump at it. That would just be so good. Oh, you can jump at me.
I don't trust you not to do something dumb. I don't know if that's smart. But yeah, I'm happy to leave it on, and when we come back, grab a bike to come back. Anyone who wants to can drive it around. It's really cool. Even before it does truly interesting things, it's a lot of fun.
I'd say that was true.
Alan, can you hear me?
Camera view, though, so you can send it out of your.
Alan.
How's it talking to VO?
Yes, posting it after.
Somebody is asking a question online. Go ahead.
Hi, can you hear me, Alan?
Yeah.
I missed it. Where did you get this robot from? Did you buy it or something?
Yeah, I ordered it from Unitree. I actually ordered it at the end of last year. After epiphany that if I allow myself to get bored, interesting things will happen in my mind. So of course that means I purchased a dog. And it took so long to ship that I actually imagined, ordered, and built Alfie while I was waiting for it to get here. And then the Alfie was done at the same time the robot got here, and I'm like, what should I work on first? But yeah, ordered.
Wow, that's really cool. I wish I was there.
Yeah, man, you'll have to make it up at some point.
So there's a speaker, gonna get big sound.
The air version doesn't come with the speaker, but you can package it.
That's a demo or something.
Yeah,
That's what you were meant.
Yeah, for show and tell.
And once you push
Should
it,
it be an indoor one?
I mean, we can do the same thing with the phone.
sport mode, yeah, no. Very easy to. What is the
Yeah, the indoor one is. I could skip it or my family. That's one.
Yeah, the
Like I showed the video.
So I would imagine that's all right. It's on full Wi-Fi.
But you're not gonna walk 3 blocks from your house where they play your signature.
Oh, I don't do that. But there is a CMCIA slot for a cellular modem, so there are more advanced control methods possible if you want to select it.
Wow.
Yes, should be able to.
Oh, that's awesome.
All right.
That's so cool.
Oh, you guys posted things.
Thank you, Alan.
Hi, Ben. How are you?
Hey, let me leave this and go back in the room.
Well, I start working at Disneyland next weekend.
All right.
Tim, are you working at Disney now?
That's every day.
Is that a yes?
Yeah, my first work is next Saturday.
Good for you.
I'm sort of very excited about it, as you can notice.
Yeah, no, that's awesome. Magic Kingdom.
Yep. Nice to see you again, Camp.
It's good to see you, buddy.
Hey, that walking robot, that dog robot was really cool looking.
Go to Unitree.
Probably very expensive, I would think.
That's $1,600. Yeah, the dog's $1,600, right? Go to.
Yeah, I can't hear anybody else talking, and they must have muted the
Let me
main
find a
thing.
website.
Yeah. Hey, Bill, how are you?
Yeah, otherwise there's.
All right, Ken, you're up next.
Have anything in that?
I'm getting over
Gold.
a cold, Bartlett.
No, anybody who has anything.
Oh, okay.
Actually, no, I do know there's a lady that partly designed.
Ken, can you hear us?
Yes. Yes.
This though.
I just thought you might have something in it.
No,
What's
I was in a new Apple commercial, the new Apple.
$1,600.
First as a incinerator.
Okay, awesome.
It's a.
Tim, I'm putting a link in the chat.
Check that out.
Yeah.
So I was thinking you went.
No, that's the last time I did it.
Well, I remember when you brought in your robot signed by the Mandalorian years ago.
Yeah, I know, but like
that was that is awesome. Well,
Thank you. Guys, Camp is up next.
okay, I'm sorry.
Tim, I put that link in the chat for the go to.
Oh yeah, I will open it up and look at it here in just a second.
All right. Is it my turn?
Yes, it is.
All right. Let me share my screen here. I'm having a hell of a time with my ROS and something that used to work that doesn't work anymore, but that's why we have video. And so here is a video. Where did it go? Of here we go. Here's a video of it's actually this is a few of us: Alan Fetterman, Ross Lunan, Phil McCrary, Tom Messerschmitz are working on a project called Mock Turtlebot, where we're going to build like the original Turtlebot or even the Turtlebot 4, which is like a $2,000 robot. But we're going to build it homebrew style. We'll build it with one of 3 different type bases: the Create 3, the Botvac, or just a regular Roomba. And then we'll describe 3 or 4 LiDARs: the XV, the YP, the RP, the DL, etc. Whatever LiDAR you've got. We'll describe cameras: OAK-D, PyCam, regular Logitech just for viewing. And we've got a homebrewed ROS 2 sonar sensor that I covered in my book last year, Homebrewed Robots. It's available on Amazon, $19.95. But here you can see the one of the Mach 2. It's got a camera on there. You see that in the left. And this is ROS 2, and the robot's navigating around. That's a Create 3 base with a DL06 LiDAR and a Logitech C270 camera. And as you can see, I'm nicely navigating from one department to the other. I'm having a hell of a time now, though. When I launch Slam Toolbox or the localization launch file, all of a sudden my scan disappears. So I've gone around the horn. I'm not going to go around here on it. I talk about it in my ROS discussion group on Tuesdays a lot. But anyways, when we figure it out, it's going to be great. And so here are the robots basically navigating back and forth. This is in ROS 2. This is waypoint following, where I've set several waypoints back and forth from one end of the room or the other. And here you see the robot just going back and forth. So that's really all I've got right now. Let me exit this. But like I say, we're working on a project. I know what I wanted to say. let me share the screen one more time, is that in the category of it's easy for me to spend your money, I really recommend the Create 3. I think this is an awesome robot. It's all built on ROS 2. So when you get a Create 3 and boot it up, basically it's a hotspot and you put it on your Wi-Fi. But the point is that when you boot it up, it's running these ROS nodes, and out of the box you can run teleop keyboard and drive it around. I Velcroed a DL06 LiDAR on there, which has a ROS 2 package that includes a base laser to base link transform. And so it's like you can Velcro the LiDAR on there and drive it around, and it starts mapping out of the box. That's mapping, not napping. And so, but arguably the Botvac is the best value, because you can get Botvacs with the LiDAR on eBay for like $150. Whereas with the Create 3 for $450, you got to add $100 LiDAR, and by the time you add the Pi and your camera and so on and so forth, you're into it for $600 or $700. So, the thing's like $1,000 retail. The TurtleBot 4 current from ClearPath sells for $2,200. But with a Botvac, which includes the LiDAR, you add, camera and sonar sensor, the Pi, etc. It's like you can build a Create 3 equivalent for around, $350, $400, something like that. So that's what we're currently working on, the mockers, and it's the mock TurtleBot. And so stay tuned.
Thank you, Cam.
Right on.
That's all. Thank you very much.
Keep up the good work. All right, I believe Jim was outside. He wants to do the demo of Truckasaurus.
Oh, good. Okay.
I will be leaving early because I have to take a social bank. But I will see you guys next month. And Alan, can you do your phone too?
Yeah.
All right, guys.
Sure.
What's going on here? Is this a lunch break? Is this the lunch break, Jim?
Hey, Alan. Hello.
Hello. Anybody out there?
All right, there we go. We got audio back. Camp, I can hear you 4x4.
Oh, is this the lunch break? Is that what's going on?
We're switching to mobile for a second, so we can watch Truckasaurus.
Yeah, Jim is doing his demo before lunch. So, well, it's going to benefit the people online. I also. So,
Oh, by the way, your your link didn't work.
Let me try it again.
Okay, so
all right, so
right now we got a good map here. But people can see the match of this.
Shoot, I grabbed the wrong one. Be right back. Hold on, Jim, 1 second.
Tim, try that link again. It's going through for me.
All right, I'll try it again.
Where is me? Where is me? This is me. There we go. Okay. All right. Now we're cooking with gas.
And robot does not respond very well
Right, too many messages.
Sneak in here for a second.
It's the problem we have, when our is on,
Hey, guys, see you next month. Thanks.
Oh, you're off. Oh, okay, okay. Okay, no problem. So let's see what we got here. I'm going to switch back.
Well, it's not going through on my end, Cam.
Now we're automatic. Right? Now let's see. Now what I have to do is launch the nav step. This is all, this is the indoor version of Truckasaurus using the LiDAR, no GPS, and using the nav stack and reliant on the map. And I just generated this map of this corridor, and now we're loading up the nav stack. So it will have the local planner, global planner, and inflation zones and all that stuff.
Do you save your map before loading in nav, or you just loading in nav while you're running the SLAM toolbox?
No, yeah, this is I'm not actually running SLAM toolbox for it's just the SLAM tech mapper. So it this is all the mapping is on board that hardware.
Okay, so you're running that while you run the nav2 stack.
Yeah, it's simultaneous. It's parallel. It's in parallel.
Okay, and you've just loaded in the nav2 stack now. I see the inflation layers.
Yeah, so now they take a while to come in, and now you see that this navigation active, localization active. So now let's try to do a nav goal. But what I like to do is relative to one first. And what I have to do is hold down this. Let's see.
Well, that's a really good looking map.
Yeah, this has just been created just now. Oh, it's that proverbial problem that's stuck in.
You need a rear bumper.
So now you can.
I see you walking.
And when you walk, you leave an imprint of the where you were in the local planner, obstacle avoidance, so that this eventually will go away. But yeah, now it's having.
There's a parameter in nav2 that you set to make it go away, right? There it goes.
Yeah, it'll go away at some point.
Did that go away automatically there?
Yeah, it's automatic. So now it's going to its destination. Again, with I like to turn off the nav. If I had time to plan, I would save some points. Actually, I wrote software that you can click some points and save some points to a file, and then you can run the course of those points, which is better because, like I said, there's a big problem with this. RViz produces so many messages, it causes the robot to have problems. So it's better just to turn it off. And I don't know how to fix that really, but like here, let's put another one in. Maybe I think.
Is it delocalized right now?
Is it delocalized?
Yeah, looks like there's a wall there that wasn't there.
Yeah, that's a good question. Oh, it's not. Yeah, it's seeing the wall.
Yeah, it's not sure of the glass. It looks like it's kind of picking up the exit.
Oh, that's the exit. Yeah, but before it was. I don't know.
Do you need to reset the pose further up? There you go. Go the other way.
I should rotate this mouse.
Those path following lines look weird. I wonder if that's the slam tech.
No, that's the Slam Tech doesn't have anything to do with those. That's the MPPI controller, and they are designed to be that way because it's an acronym. It has to do acronym planning will have these very like pointy looking plans because that's what a 3-point turn looks like, or 2-point whatever. A multi-point turn has a little pinch point. Okay, so now it's going to where I'm trying to go to a new destination. Actually, these are all the people. So I tell it to go, let's try to squeeze it over here. Good enough. You'll see, yeah, it makes a little
Which uses up one of your hands, so it's hard to control.
That's why you have it. Yeah, safety first.
We made ours optional, so whatever position you start in, like this.
Yeah, only for testing. When we do contest runs for Magellan, the safety is fully engaged camp. Don't worry.
Yes, if I turn off RV's robot open page, it will go a lot better.
Interesting.
So one of the things I had to do was increase the throttle when the robot's turning. This became an issue I had to discover just by trial. So when this robot has got an angle of turn, the throttle, you naturally, when you're manually driving it, you increase the throttle because you see the robot slowing down. Well, I had to add that to my throttle equation. Convert your input is going to be the nav stack will tell you I want a twist of X rate of a certain X rate, and that you need to convert to RPM, and we'll eventually need to convert that to like PWM signal to the motor. So I had to put a put part of the equation in there to take in the steering angle and multiply up the throttle, compensate for that. It's like really there's some internal part of the drivetrain is some friction or whatever, and so you have to push it harder to make the turn. I think that's what you've done.
Does it have a lock differential? No.
On this one, I don't. I'm not sure about that. So let me notice it performed a lot better when I canceled. If somebody anywhere here knows like a why or a way around, or maybe I have to modify my firmware so that it doesn't have this pause problem. That, like because it's somehow when all these messages are coming from the bar bids, that it is getting stuck somewhere in my firmware code. It's not getting to the motor loop update. Yeah. And I haven't tracked this down because I didn't care that much. But for demos, I guess it's kind of good.
So are you running nav2 on the robot or on your computer?
Yeah, it interrupts. Well, say again. I don't know if I want to implement all that, just hard.
Hey, Jim, are you running the navigation stack on the robot or on your workstation?
Navigation stack, it's on the robot. Yeah, you could also run it on the workstation as well, but I want everything running on the robot naturally. For the contest. Let's do, yeah. This Okay, let's try again. I'm going to give it a longer. Yeah, I run everything locally when I can.
Well, that's cool. So you can kill RViz and it still navigates, hopefully.
It does. In fact, like I said, I have a program. I'm just not quite ready in this under this kind of time frame. But I can click. I have a program that will a Python script that I can use the 2D pose estimate and click on it several times and record a path I want or waypoints, and then I can just run the script or run another script to say follow those waypoints and no RViz involved. But like, for instance, let's give it another nav. Where's the point? I want to go the other way. So I want to go back over, here's the, yeah, now, okay.
So here you're driving it with teleop keyboard, right?
What's that?
There you were driving it with teleop keyboard, right?
No, that's not driving. This is all autonomous. I'm not doing any driving.
Oh, really? Okay.
It's all autonomous. So try again to go more towards people. Just like sometimes I want to get rid of the RViz. Okay, let's do one way over here. Yes, now it's working. I don't know why. Which I think RV is running is, and you can even navigate between people pretty. Nobody moves there.
Yeah, you got pretty good swing.
Back now over here. So yeah, now it's reaching its goals. You know, I just kind of quit RViz and relaunch.
Yeah. When in doubt, reboot.
But I mean, there's definitely a problem with messaging. Kind of polluting. Okay, let's go this way now. Now I can come back. Let's come back. Because I'm setting autonomous. You guys can see my screen, right? I mean, I'm publishing, right?
Yep.
And you know,
you pop down the global op. You're running a map frame, right?
Yeah, this is a graphic. Okay, now I'm gonna have it come back. See how it slows down there? And now it's kind of roughly navigating between people.
Yeah.
Right. Oh, it's working better.
Beautiful.
All right. Well, any questions? No.
No, man, looking good.
Thank you. The next step is outdoors. And yeah,
All right, so that concludes our meeting proper. I'll stop the recording.